Welcome back. I am absolutely thrilled you're joining us for this explainer. Today, we're diving into something that literally touches every single one of us, yet it usually operates completely behind the scenes. We're going to uncover how educational experiences are meticulously engineered. Think of it much like a structural blueprint for a skyscraper. A great class doesn't just happen by accident, right? It's designed from the ground up.
To get a feel for this, take a look at these balancing rocks. It perfectly captures the core challenge, doesn't it? A curriculum has to flawlessly support a student's cognitive growth, carefully balancing the heavy weights of knowledge, skills, and values, all without collapsing under the pressure. If just one stone is off-center, well, the whole structure falls apart.
All right, here is our roadmap for today. We're going to break down the 6 load-bearing pillars of curriculum design: the blueprint of learning, alignment and continuity, sequencing the mind, connecting the dots, relevance and balance, and rounding it out with the flexible foundation.
Now, our master blueprint relies on what's called a coordinated curriculum system. Just look at how all these separate pieces seamlessly interlock. You've got backward designs sliding right into vertical and horizontal alignment, which then locks perfectly into personalized learning and flexible pathways. None of these just float around in a vacuum. They form a cohesive, unified system that guides the entire educational journey.
Section 1. The Blueprint of Learning. Foundations laid down by Tyler and Taba.
Section 2. Alignment and continuity, the structural pillars.
So these first 2 pillars, absolutely crucial for making sure students actually learn what they're supposed to, and more importantly, that it sticks over the long term. First up, we have constructive alignment. The idea here is that learning outcomes, teaching activities, and assessments have to be perfectly aligned. Think of it like a 3-part combination lock. The goal you set, the activity you do in class, and that final test must all fit together flawlessly. If you teach one thing but test another, the structural integrity of your curriculum just fails.
Okay, let's dive into this with some concrete examples. In math, if the goal is to solve linear equations, the classroom activity is guided practice on those equations, and the test is, well, a quiz on solving them. Over in science, if the outcome is to explain photosynthesis, the activity might be a hands-on lab experiment, followed by a test where the student draws a detailed structured diagram. The pieces always have to match the goal.
And that brings us to continuity. Basically, this means key concepts are revisited over time to really deepen that understanding. It treats core ideas as a solid foundation that you just keep building on, layer by layer, year after year. You don't just memorize a concept for a test and abandon it. You keep coming back to it with a wider and wider lens.
To really see this in action, think about a student's journey. A math student learns basic fractions in primary school. Then, years later in secondary school, that exact same foundation gets stretched into complex algebraic fractions. In science, you learn the basic idea of a push or a pull, force, early on, but eventually that expands into the rigorous mechanics of Newton's laws. The learning is continuous and ever-expanding.
Section 3. Sequencing the mind, building cognitive steps.
Take a second to think about this. Why did you have to learn basic addition before tackling calculus? Why simple subjects before complex ones? It's not arbitrary at all. It's by design. Sequence dictates that content is arranged from simple to complex and from concrete to abstract. And here's a fun aha moment for you. This principle is directly linked to Jean Piaget's famous theories of cognitive development. You literally cannot teach the abstract until the brain firmly grasps the concrete. The curriculum has to mirror the biological development of the human mind.
Let's look at how this builds mathematically. We start a step-by-step cognitive climb at step 1 with highly concrete basic numbers. Once you master that, we move to step 2, operations, like adding and multiplying. Then, boom, we take a huge leap into the abstract with step 3, algebra, before finally hitting the peak complexity at step 4, calculus. You just can't skip a step without tumbling down the stairs.
And we see a beautifully parallel timeline over in science. We start at point 1 with basic observation, literally just looking at the world. Then, point 2, we organize it by classifying things. Point 3 brings in active experimentation. And only after all those steps are mastered do we finally arrive at point 4, advanced scientific theory. It is a very calculated, logical progression.
And this graphic brilliantly illustrates how these concepts swirl together in practice. In a targeted math learning experience, notice how core content like number and algebra, or measurement and geometry, is wrapped tightly by essential proficiencies, things like problem solving, reasoning, understanding, and fluency. The sequence of content is constantly being engaged by these dynamic mental skills to create a really rich learning experience.
Section 4. Connecting the dots. Integration across subjects.
Now, as students climb those cognitive steps, we have to make sure they aren't just climbing in a dark, isolated tunnel. That's where integration comes in, connecting knowledge across subjects and real-life contexts. Instead of keeping math locked in the math room and science in the science room, integration builds essential bridges between different disciplines. It proves to the learner that, at the end of the day, all knowledge is fundamentally connected.
Consider these examples. When a student uses mathematical graphs to analyze experimental data they just collected in science class, that's integration. Or think about a STEM project where they have to design a bridge. They have to flawlessly integrate the geometry they learned in math with the physics principles from science so the bridge doesn't, collapse. It brings the learning to life.
Section 5. Relevance and balance. Engaging the real world.
Bringing learning to life perfectly transitions us to our next structural keys. These two principles are the ultimate drivers for student motivation. Relevance means the content actually has to relate to students' lives and societal needs. If you teach math through budgeting, interest rates, or interpreting real-world data, their engagement absolutely skyrockets. Same for science. Teaching the mechanics of climate change, human health, or sustainability connects the classroom directly to the world outside their window. They learn it because they see why it matters today.
But relevance alone isn't quite enough. We need balance. The curriculum has to balance knowledge, skills, and values. In math, that means balancing pure conceptual understanding with actual procedural skills and dynamic problem solving. In science, it's balancing scientific theory with hands-on experimentation, and crucially, an ethical awareness of how that science is used. We aren't just memorizing facts here, we're dynamically building capable, ethical citizens.
Section 6. The flexible foundation. Adapting to learners.
So we have this highly structured, meticulously aligned blueprint. But what happens when the actual students walk into the room? Well, a rigid blueprint has to be adaptable to the very real, very diverse people using it. Flexibility adapts the curriculum to the learner. In math, this means differentiating tasks so different ability levels can access the same core concept in a way that challenges them appropriately. In science, it might mean adjusting an experiment based on what resources a school actually has. The crucial point is flexibility ensures the blueprint works for everyone. It makes inclusive education possible.
All right, let's pull everything we've talked about together into one core summary. We have constructive alignment matching outcomes to teaching and testing, continuity revisiting concepts over time, sequence moving from simple to complex, integration connecting subjects together, relevance tying lessons to real-life contexts, balance harmonizing knowledge, skills, and values, and flexibility adapting it all to the actual learners in the room. This right here, this is the permanent educational blueprint.
Which brings us to the ultimate question. You now know the hidden architecture behind how you were taught. So if these principles built the curriculum you learned from, how might you step into the role of educational architect to redesign it for the world of tomorrow? How would you balance those stones? Think about it. Thanks for joining me on this explainer, and keep learning.